Hello everyone. In this video, we're going to go through an overview of Chapter 6, Sampling Distributions. My name is Fred Rispoli. So the quick overview is we're going to talk about populations and samples, distributions of the sample mean, the central limit theorem, the distribution of the sample mean when sigma is unknown, which leads to the t-distribution, and sampling distributions for the variance. This will lead us to the chi-square distribution and the F distribution. So I'll begin with populations and samples. As you probably already know, we consider a population the vast collection of all potential observations of a particular type. For example, perhaps we want to know the enrollment figures of the freshman class at Stony Brook in the year 2019. Or perhaps we want to know the heights of all male students at Stony Brook University. So these would be populations, but typically they're very large. So we often focus on a sample. Now a sample would be a data set that's acquired through the process of observation. So one example might be, suppose we're interested in an election. So we'd like to be able to predict how people might vote in an election. Perhaps it's an election of the president or some other similar situation. So it would be very expensive and time-consuming to try to get the opinion of all voters in the United States. So instead, we may take a random sample of, let's say, 1,500. Now, from that sample, let's say we find that 600 people polled support candidate A, then we would sort of put together what's called a sample proportion, P. So it would be a fraction where the numerator is the number of people that support A over the total number in the sample. And from this, we'd figure out that the proportion or the percent of people that support candidate A, let's say, is 0.40 or 40%. So this is done all the time in statistics, and we need to distinguish between parameters and statistics. So we'll say that a parameter is some characteristic that's obtained from a population where we're considering every item in the population. And for parameters, we'll use the Greek letters. So mu, for example, would be the population mean, sigma squared, the population variance. And we'll define a statistic as sort of a function of one or more random variables obtained from taking samples. So we might think of a sample mean, for example, and we use a sample mean to try to provide an estimate for the population mean. So in that sense, we distinguish between parameters, right? That's a characteristic of a population. And a statistic is a number that we get from taking a sample that's used to help us predict a population parameter. Now, in doing this process, we need to understand the behavior of sample means and sample variances, for example. So suppose we have a random sample of size n. Okay, so the items in that random sample we'll think of as x1, x2, and so on up to xn. Okay, and let's say they're obtained, or the random sample is obtained from a distribution with mean mu and standard deviation sigma. So now consider repeating this process over and over again of taking sample means. And we end up with an x1 bar, an x2 bar, and so on, an xk bar. So we might be taking samples of, let's say, size 5, but suppose we did that 100 times, okay? And then we create a histogram for these sample means. So the question that we want to be able to answer is, what does that distribution look like? What's the shape of the histogram, okay? What type of mean do we get from the sample means, right? The mean of the sample means. What type of standard deviation do we get for the sample means, okay? So we're very interested in, what can we say about this distribution? Well, one thing you could say is that think of this sort of as the mean of the sample means. It's the same as the population mean. All right, nothing very surprising there. That's what you might guess. But what about the standard deviation of the sample means? Okay, or the variance of the sample means? That's where we start to see a difference. Okay, the variation of the sample means is the population variation. So if you just wanted to guess, you might just guess this numerator, but that would not be correct. The answer is the population variance divided by n. Okay, so the variance actually goes down. Okay, remember n is the size of the sample that you're taking. What's the standard deviation of the sample means? I call this the sigma sub x bar. Well, this is the square root of this variance. It's sigma over the square root of n. So you could see the standard deviation does change. Okay, we have to take the population standard deviation divided by the square root of n. Okay, so here's a little graph to sort of show you what's happening. So let's say we're taking random samples. Okay, we're taking random samples from this sort of original distribution. You can see it's somewhat symmetric. It looks like a normal distribution. So if we're taking random samples of, let's say, size n, where n is 4, we would get a distribution that might look like this. You could see it's a normal distribution, but it's much tighter than the original distribution. Or in other words, it has a smaller standard deviation. Okay, and you could see as the size of the sample goes up, so if we go from 4 to 16, then we get this next bell-shaped curve. Okay, so it's much narrower, and the standard deviation is even smaller. Now we take the population. Remember, we divide by the square root of n. So here we'd have the original population divided by 2. Here we'd have the original population standard deviation divided by 4. And then if we go up to samples of size 64, you get this very narrow distribution over here. Because now we're dividing the original standard deviation by 8. Okay, so we sigma over the square root of n. So you can see this distribution of sample means looks bell-shaped, but it gets narrower and narrower as the sample size goes up. So here's another way of saying it, is that the standard deviation of the sample mean decreases as n grows, even though the mean stays the same. So you can see that in those previous pictures. The mean was the same. So yet another way to say this, the distribution of x bar tends to become more concentrated around x bar. So you could think in terms of the more information implies more certainty about the estimation of mu. And we could say this in a more formal way, that x bar, or this distribution of x bar, is normal when sampling from a normal population. If we have x1 through xn as a random sample from a normal distribution with mean mu, variance sigma squared, then x bar will also be normal, mean mu, variance sigma squared over n. So here's another graphic similar to what we had before. So this red bell curve, that might be your original normal distribution. When we're sampling for small n, we get this blue curve. You can see it's narrower than the original curve. And when we have large n, we get another normal distribution, all with the same mean, but this one is even more narrow than the one with small n. So what about when we sample from distributions that are not normal, right? In the previous two slides, we were sort of assuming the original distribution was normal, okay? But the surprising thing when you first start studying statistics is that we get the same results even if the original distribution is not normal. This is sort of the interesting part of what's called the central limit theorem. So we'll start over here. If a random sample of sufficiently large size is taken from a population with any distribution, with mean mu and standard deviation sigma, okay, so imagine we have some crazy distribution that looks like this, then the distribution of the sample mean is approximately normal. Okay, so sampling from this distribution could lead to this distribution for the sample means. Okay, and we know that the mean of the sample means is equal to the mean of the original distribution, and the standard deviation of the sample means is the same that we said a couple slides ago, sigma over the square root of n. So that's very sort of surprising. And this graphic over here sort of tells us the same thing. If this was our population, this purple region that we're sampling from, then for large enough n, we'll get something like this. And typically, the sufficiently large size is 30. If you're taking samples of size 30 or more, then the sample mean becomes normally distributed, at least approximately normally distributed. So here's one way that this plays out. Okay, let's say this result, the central limit theorem, will be important in some of the statistics we'll do later on in the course. But for now, here's how this might play out, and here's a good way to think about this with some various probability examples. Let's say X is normally distributed with mean mu equal to 84 and sigma equal to 14. So if I want to know the probability X is between, let's say, 82.6 and 86.8, we could approach this the way we did in chapter 4. Find the z-scores for 82.6. So I have X minus mu over sigma, and same thing over here. So this gets converted to the probability z between minus 0.1 and 0.20. Look up the values in the table. Out comes your probability, 0.1191. Now, suppose we ask the same type of question, but for a sample mean. Right? So when you look at this versus this, the difference is here I just have an X, you think of it as an individual value, but here I have a sample mean, which changes things quite a bit. So if I have a sample mean, well, I must have a sample size. So let's say n is equal to 49. Suppose that's our sample size. Okay. So now when I go ahead and make this calculation, my standard deviation changes. It's not the 14, right? This was the original population standard deviation. I have to use the standard deviation for the sample means. So here I use sigma over the square root of n, 14 over the square root of 49. Square root of 49 is 7, so we get 2. Okay, so I purposely put this in red because here is the important difference. But now, look what happens to the probability. We go ahead and find this probability, and even though I have the same lower and upper bounds, let's say, on this interval. Okay. Now down here, when I find the z-scores, I use 2. I use 14 over the square root of 49. Okay, both places. So this changes the probability quite a bit when I work this out. My probability, the sample mean between these two values is 0.6772, right? So the individual, 0.1191, the sample mean, notice that this goes up, okay? So maybe you could imagine a couple of those graphs that we saw before. We may have a normal distribution for an original population, but now we're going to have a much tighter, narrower distribution. So the probability goes way up. Okay, so there's also some cases where you don't know the population standard deviation. Okay, in that case, we have to sort of change the distribution we're going to use to find out about some of our probabilities. So for example, if x1 through xn is a random sample from a normal distribution, and we know that the sample variance is equal to this sum. So this is just the formula for our sample variance. Then t, we set this equal to x bar minus mu over s divided by the square root of n, follows a t distribution, and we say this with n minus 1 degrees. So the t distribution, okay, is really a set or a family of distributions that depend on the degrees of freedom, which, remember, this is really just a function of the sample size. And there are some interesting properties here, so let's go through them. The first one is that the distribution is still bell-shaped, symmetric about 0. Okay, so these are some curves. This very top curve is a normal distribution, mean 0, standard deviation 1. The second property is that the t distribution curves are more spread out than the normal curve. Okay, so we could think in terms of either more spread out, or I like to think that they get sort of flatter and flatter. But as they get flatter, the tails get wider. Okay, so the amount of area in the tail here for this red curve is much more than what you see with this black curve. So that's sort of what we're saying here. Now this is the Greek letter nu. We use nu sometimes for the degrees of freedom. As nu increases, the tails become thinner. Another way to say this, as the degrees of freedom get larger, the tails become thinner. As they get smaller, the tails become fatter. And as the degrees of freedom approaches infinity, these t distribution curves approach, let's say, a standard normal distribution. Okay, and when the degrees of freedom is 30 or more, then you get pretty much, the same results that you would from a normal distribution. So the origin of the t distribution is quite interesting. This distribution plays, an important role in a number of important types of statistical studies. And you might see this described as the student's t-test for assessing the significance of the difference between two sample means. Okay, why does it get called the student's t-test? Well, it's very interesting history here. It was developed by William Gossett, and he used an alias, right? He actually wrote statistical papers that investigated the t distribution but he wouldn't put his name on it. He would just call it student. Okay. Why did he do that? Well, Gossett worked at a brewery in Dublin, Ireland. In fact, it was the Guinness Brewery, and the company did not allow him to publish statistical papers, especially when it was based on statistics that he was using at the brewery. So he often made studies, right? He was a quality control person, and he made studies. He was studying the chemical properties of barley where sample sizes were small, maybe size 3, 5, 10, okay? And the standard deviations were not known, so he always used the sample results, okay? So he performed these experiments for the Guinness Brewery, so it was interesting. He was, deep down in his heart, he was a statistics researcher, but he also worked at the brewery. And that's why you'll sometimes see the student's t-test associated to the type of test we were talking about. Now, it'll be important to learn how to use the table for the t-distribution. So I show it to you here. You can see the table is based on, these would be the degrees of freedom, and the values that you get in the table are based on some alpha amount. So a certain t value is obtained when you look at, let's say over here, suppose I had degrees of freedom 11. Okay, so we'd end up using, well, over here, degrees of freedom 11. So this value here, 1.796, would be the value that gives you an area of 0.05 in the right tail. Okay, so these are t values that give you a certain alpha amount in the right tail. So in a way, it's just the opposite of the way the normal distribution tables work. The normal distribution tables always give you the area to the left, but the tables that we're going to look at really in this chapter, okay, give you, well, the t values in this case based on a certain right tail area. Okay, so we were talking about sampling distributions for sample means, but it's also important to consider the distributions you get from the variances. So what you see here is a histogram, okay, for a simulation that I ran, okay, and I was taking samples of size 5 from a normal distribution, standard normal distribution, right? Mean 0, variance 1. So I generated many random samples, okay? Random samples of size 5. And then I took a look at the variance and created a histogram. So what do you expect? Well, you don't get something that's normal, okay? You get, see, these were samples of size 5. So this was my distribution. You can see we have this one almost looks like an exponential over here. And then this was another run. I used 500 samples to create the histogram. So you could see this one's not quite exponential. So it goes up and then it goes down a lot. Okay. So what we get is a distribution called the chi-square distribution. So the idea behind the chi-square distribution is if you're taking random samples of size n from a normal distribution, and then we look at this, think of this as a random variable if you want, we take n minus 1 times the sample variance divided by this population variance. Well, this turns out to follow what's called the chi-square distribution with degrees of freedom n minus 1. So the curves for the chi-square distribution may look something like this. You can see in general they are not symmetric. Okay, they tend to go up a little bit and then they go down in a nice skewed way. When the degrees of freedom is high enough, then they tend to be more symmetric. So what you need to understand is there's also a table that we're used to get important values. So we'll have to do this in the later chapters when we start looking at confidence intervals for a variance and do some hypothesis testing. We'll have to use a table like this. And again, this gives you values of that chi-square statistic, right? Gives you values for this value here, based on a certain area to the right of alpha. Okay, so we want to think of these are based on right tail probabilities. Okay, and the last distribution that we'll mention is based on the ratio of two variances. And to study this, we use the F distribution, right? The previous distribution we just looked at was based on just one variance. Sometimes we want to test to see if a certain variance is equal to a target value. That's where we use the chi-square. Other times we want to see if two different independent variances are equal to each other. That's where we use the ratio of the two and the F distribution. So if I have two different sample variances, let's say taken from two different normal distributions, okay, and I look at the ratio of S1 squared over S2 squared. So this is the ratio of the two sample variances. Then that's known to follow an F distribution. And now I have two degrees of freedom. Degrees of freedom 1 and degrees of freedom 2. They're both, an n-1 value. So again, if we were to graph the F distribution, we get different shapes depending on the degrees of freedom. So it's important to pay careful attention to these two different degrees of freedom. And there's an important identity that I will mention. If we have, let's say F follows this distribution with n1 minus 1, n2 minus 1 degrees of freedom, then 1 over F follows the distribution you get when you sort of flip these two degrees of freedom. This is n2 minus 1 and 1 minus 1. So this identity is important because we'll have to use this to get certain values from the F distribution. And there are various tables for F distributions. This is a table that gives you values, but all based on alpha is 0.05. If alpha was 0.01, we'd have to use a different table. Okay, and some newer versions of these tables try to incorporate values for different alphas. Again, here, this one is just for this one alpha value. So this is the start of these sampling distributions in Chapter 6. In Chapters 8 and 9, we'll have to use these distributions, as I said. It's good to get some practice now. So taking a look at some of the practice problems will help. Some of the solved examples will also help. So that's it for now. I hope you found this video useful.